Okay, let's talk about transistors. So transistors have four different working modes: fully on and fully off mode, which we can say the transistor is fully saturated. And we have the forward active and reverse active, which we can say the transistor is in the active region. So basically means the transistor is partially on. The saturated mode works as like a switch. So it's used in digital circuits, and in the active region the transistor is controlling the current. So it's mostly used in the analog circuits for amplifying purposes. Since we are building logic gates, we have to work with the saturated mode because it's going to be either on or off, which will represent the ones and zeros. So here you can see PNP and NPN BJTs. To turn on an NPN, we drive a current to the base, NPN turns on, and we have a current flowing from collector to emitter. To turn it off, we give the base no current and it turns off. And for PNP, if current is coming out of the base, the transistor turns on, and if there is no current, again, the transistor is off. So how do we give this current or pull this current from the base? How does that work? So let's look at this NPN case. We want to drive some current through this load. As you know, the current flows from high voltage to low voltage. And what we are trying to do is pushing a current from base to emitter. We have a 0.7 volt drop from emitter to base because it's basically acting as a diode. So with the 5 volt we have on the top, if we close the switch, we're definitely going to have some current flowing to the base. But this is wrong because we have too much current flowing to the base. So it's gonna ruin the NPN, and it might even ruin the battery. It might even catch on fire. Everything gonna catch on fire. So this is just not good. So what we have to do is put a resistor here. So we limit the current flowing to the base. So what resistor value should we pick? We can pick something low because if there's too much current passing through, it's gonna ruin the NPN. If you pick a high value, the transistor will be in the active region. As we saw previously, transistor had 4 different modes. And if we are not giving enough current to the base, then this transistor won't fully turn on. So we have to give it enough current so this transistor fully turns on. We don't want it to be partially on. We have to first calculate how much current is going through the load when the transistor is on. When the transistor is on, we usually have 0.2 volt drop across the transistor, or even less. We usually ignore this 0.2 volt drop, but I'm just going to include it. From Ohm's law, we can find the current to be 5 volt minus 0.2 volt divided by the resistance amount. So we said that the load is just 1K. So we have this much current going through the transistor from collector to emitter. Transistors have a current gain beta. In this case, my transistor's current gain is, let's say, 15. So you can put 15 times less current here and 15 times more gonna go through the transistor. That information, we divide the current we found by 15. So we have to drive this much current through the base to turn the transistor fully on. Okay, then let's calculate the resistance again. From Ohm's law, we would have resistors equaling to voltage divided by current. And we had 5 volts minus 0.7 volts because we had a voltage drop across the transistor. And we would get this value. So we need this much resistance to fully turn on the transistor. But there is also a catch. You wouldn't want to pick 13.5 kilo ohm resistor. You would most likely pick 10 kilo ohm. We pick 10 kilo ohm because we want to give more currents just in case there is some fluctuation in the current gain value provided by manufacturer. So they say 15, but maybe it's actually 12 or 17. So we give more current to just make sure the transistor is fully saturated. And here's the PNP case. As you can see, it's the same situation. We first calculate the current going through the transistor, and then we calculate the base current based on the gain value. Then we calculate the resistance, but then we make it a little bit less so we know for sure enough current going to pass through the base and saturate the transistor fully. You might have noticed that instead of load being on top here, it's now here, like how it was in the NPN case on the top. It's because the location of the load kind of matters. Now in the PNP case, it's going into the emitter and coming out of the base. So first of all, we want a voltage difference between this location and just this location. So we have 5 volts here because of the wire connecting here. And now we have a 0 volt right here. And when the switch is closed, then we get some other voltage here, which would be probably 4.3 volts. Because of the 0.7 volt drop, and the rest of the voltage drop will be across this resistor. If you look at this side, now we get a 4.8 volt drop across the load, and then we have 4.8 volts here. Then we have a 0.2 volt drop across the PNP transistor. But if you had the load right here, then it would have been completely different. Then we would have had a 0 volt here and then 0.2 volt here because we have 4.8 volt drop across the load. Now it's not going to be fully saturated because we don't have enough voltage across here and probably not enough current because we don't have enough voltage going through the base and fully saturating it. So if you put the load on top, that's going to be for some different scenarios that I'm not covering in this video. So if you're using the transistor as a switch, you should put the load on the collector side. And in the NPN case, we had the load here. So we were getting a 0.2 volt somewhere up there because we had a 4.8 volt drop across the load. Then we had 0 volt here. And because of this 5 volts, we were getting enough potential across here to drive a current through this route from the base. But if we put the load here, we get 5 volts here because this is going to be essentially short. And so we get 4.8 volt drop across the load and we get 4.8 volt at this point because it's right after 0.2 volt drop. So now we again have the same issue. We don't have enough potential difference across these 2 points to make the 0.7 volt drop and probably not enough current going through. So the transistor is not going to be fully saturated and is not going to behave as a switch, which is why you should put the load on the collector side. Okay, let's talk about pull down resistors. So far I showed you an example with a switch, this switch right here. But now I'm just gonna use a jumper wire to demonstrate this problem. So when the switch is open, which would be when the wire is not connected here, we have a floating base, a floating voltage right here because it's not connected to anything. So with a floating base, the transistor might partially turn on and we don't want that. To solve this issue, when the wire is not connected, we add another resistor here with a much higher value, like a 100k resistor, to solve this issue. So when the wire is not connected, this resistor going to make the base voltage 0. So now we for sure know the transistor going to be fully turned off, which is what we want. And after we connect the jumper wire to 5 volts, now the current is flowing this way. We have a tiny bit current going to the 100k resistor, but that's very tiny because we have a very high resistor. So now the transistor is going to turn on and the current starts to flow. To demonstrate the importance of pull up and pull down resistor for transistors, I built this test setup and now I'm measuring the collector of an NPN transistor with no pull down resistor. So we are reading 5 volts. It's open, so the transistor is off. We are reading 5 volts on the collector side, which makes sense. This is how it looks like on the oscilloscope. The moment I touch the wire, look what happens at this and there. So the transistor is partially turning on. That's the reason why the voltage is dropping a tiny bit. So the current is, a tiny bit of current is flowing. So this is not good. My hand just touching the wire is enough to do some capacitive coupling. So this is not good. That's why we have a pull down resistor for NPN and a pull up resistor for a PNP. And similarly, a pull up resistor. We have a similar issue in the PNP case. When the jumper wire is not connected, the base is floating and the transistor might turn on partially. So we add a resistor right here that's going to make the transistor base 5 volts at all times. So we for sure know the transistor going to be off because no current is coming out of the base because 5 volts, 5 volts, there's no potential difference for the current to flow. And after we connect the jumper wire, this is going to be 0 volts and we are going to see 4.3 volts here and 5 volts here. So the current is going to flow out of the base and it's going to turn on the transistor. A tiny bit of current going to come from this way, but that's fine because it's a very tiny amount of current because of the large resistor. So now you know how to operate a transistor as a switch. Thank you for watching. In the next video we are gonna build logic gates from transistors.